Hello. This lecture will cover pages 114 through 123 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 8A, AC Steady State Analysis, representing sine and cosine waves mathematically. Starting out on page 114, really page 114 through page 116, I'd like you to look at video 6D, 6 delta again, up to the 17-minute 40-second mark. That reviews the material through page 116 of the lecture notes. So make sure you look that over before we begin starting the lecture on page 117. If you look at page 117, writing mathematical expressions for the following sinusoids, I'd like you again to take a look at this, and I'd like you to write the mathematical equation for this wave in terms of voltage, this wave in terms of voltage, and this wave in terms of current, based on the values I have here for the ordinate axis and the period I have labeled in the time axis out here. And then stop the video and actually go through and work that out, and this is what you should end up with. If you notice here, I've written the voltage via t in terms of the sine and the cosine. You should be able to get that. Here I wrote this sine wave in terms of the voltage, sine, and cosine. You should be able to do that. And down here in the bottom one, I wrote this waveform in terms of the cosine, the current in terms of the cosine, and then I put it in terms of the sine. You should be able to go back and forth here as well. It's a good exercise to write these sinusoids mathematically, so we have an equation to work with. We're going to start here on page number 118. You could look that over. Sample exercise on page 118, pretty easy to understand. The phase relationships, again, we talked about those in that video 6D. And that takes us to page 120. There's 4 examples I have here, and I'd like you to go ahead and find the phase angle phi between the current and the voltage. For example, number 1, between the current and the voltage. And example number 2, I'll give you the answers here, between the current and the voltage, or the voltage and the current. Example number 3, and between the current and the voltage, or the voltage and the current. In example number 4. Don't forget, as I give you these answers here, for instance, let's take this one. You can say the current leads the voltage by 20 degrees, or you can say the voltage lags the current by 20 degrees. It's stating the same thing, one in terms of leads, one in terms of lags. So make sure you can do those 4 problems. That's pretty important. Problem number 5. For the figure below, find the phase angle phi between voltage and current and determine if the unknown elements are RC or RL, and then draw the Phasor diagram. So I'd like you to take your time based on what we've talked about. You know that you take a look at this, you should be able to make your conversions one to the other, compare apples for apples. And then do a Phasor diagram. Stop the video, see if you can get an answer. If you do that correctly, this is what you'd end up with for a solution. Notice I have the current, that's given. I'm writing the current in terms of the sine. And when I do that, I end up with the current with respect to time is equal to 2 sine of 40t plus 105 degrees. And unless you can do these, you'll mess this up. You'll end up subtracting 90 degrees. Just remember to get the conversions down. Get the technique down. Now I have the current in terms of the sine and the voltage in terms of the sine. Once you do the phasor diagram, you can clearly see in the phasor diagram, here's the voltage with an angle of 150 degrees. Here's the current at an angle of 105 degrees. The phase angle is the 45 degrees. And as these vectors rotate counterclockwise, you can see that the current is leading, the voltage is leading the current by 45 degrees. Or you can say the current is lagging the voltage by 45 degrees. Same thing. Now, if you take a look at that angle, that angle is 45 degrees. And if the current is leading the voltage by 45 degrees, it means the current can't keep up with the voltage. Well, if the current can't keep up with the voltage, that circuit has to be an RL circuit. What's in this box up here has to be a resistor and an inductor, because the voltage leads the current, or the current lags the voltage by 45 degrees, and the angle between them is 45 degrees. You'll see how that works out in future lectures, but you should be able to look at that phase angle. And if you always take the phase angle of the voltage and you subtract the phase angle of the current, in other words, to end up with a phase angle, if you always take the phase angle of the voltage and you subtract the phase angle associated with the current, if that ever turns out to be a positive angle, that's going to put it in the first quadrant. And if the angle is in the first quadrant, that circuit is inductive. If you take the voltage angle and you subtract the current angle, and it comes out to be a negative value, that puts it in the fourth quadrant. If that angle was in the fourth quadrant, it's a capacitive circuit. You only have the first and fourth quadrant to deal with. And the reason for that is pretty obvious if you take a look at it here. This is called an impedance diagram, by the way. This will be inductive, this will be capacitive, and there's purely resistive. Any angle impedance, that's AC resistance, it falls on this, falls at 0 degrees, is purely resistive. And the angle that falls this way, plus 90 degrees, is purely inductive. And any angle that is at a minus 90 degrees would be purely capacitive. Anything between here would be a combination of R and L. Anything between here would be a combination of R and C. Now, if you take a look at the impedance or the resistance, notice that there's going to be an angle associated with that. So let's just take a look at Ohm's law here, see if this makes sense. The angle associated with the impedance, we'll call it Z, has to be equal to the angle associated with the voltage divided by the angle associated with the current. That's really Ohm's law if you look at it. Impedance or resistance, impedance or AC resistance is equal to voltage over current. I'm just using the angles, not worrying about magnitude. Well, you can rewrite this as the angle associated with the impedance is simply equal to the angle associated with the voltage minus the angle associated with the current. If you're just looking at angles now, so you're always taking the voltage minus the current because you're bringing it up. When you worked with polar notation, you've done that before in previous classes. So you can always get the phase angle. And the phase angle, what is it really? Well, it's the difference between the voltage and the current all the time. Never the current minus the voltage. And just happens to be the angle of the AC resistance or the impedance. So I want you to go ahead and look that over. That's pretty important. It's called an impedance diagram. But if we go back to this problem, you can see that the angle associated with the voltage we said was 150 degrees. And you subtract the angle associated with the current, which is 105 degrees, and you get plus 45 degrees. That plus 45 degrees puts the impedance angle, well, this is a phasor diagram showing current and voltage, but if you take a look at that impedance angle is a plus 45. That puts it in the first quadrant. And we said anything in the first quadrant is going to be inductive, a combination of R and L. Well, you already know that because the voltage is leading the current. If the voltage is leading the current, it means the current can't keep up with the voltage. So it has to be an inductive circuit. If you take a look at problem number 6, for the figure below, find the phase angle phi between the voltage and the current, and determine the unknown elements. Determine if the unknown elements are either RC or RL, and then draw the phasor diagram. I'd like you to do this one very neatly. Get that current in terms of voltage, or get that current in terms of the voltage cosine wave. Okay, so you have to get this current waveform, which is minus sine, two-step process here. Get that current in terms of the cosine. You might want to manipulate this cosine by adding 360 degrees to make that angle positive. You don't want to work with these big negative angles. And see what you get for a phasor diagram, and then tell me if that's an RC or an RL element inside there, based on what I just told you. Stop the video, run that exercise, and see if you get this. What I did was I took the current waveform, or the current sinusoid up here, and I converted it to cosine. And then I rewrote this voltage in terms of a positive cosine wave. Here's my current cosine equation. Here's my voltage cosine equation. I did a phasor diagram. I put the current at 53 degrees positive. I put the voltage at plus 40 degrees positive. And you can clearly look at that and see that the current is leading the voltage by 13 degrees, or the voltage is lagging the current by 13 degrees. Well, if the voltage is lagging the current, or the current leads the voltage can't keep up with the current. Either way, the voltage can't keep up with the current. If the voltage can't keep up with the current, that's a characteristic of a capacitor, because voltage can't change instantaneously across the capacitor. What's the phase angle going to be? Well, it's going to be equal to, now I say 13 degrees, but then you have to qualify that, leading or lagging. But what I tell you to do in the previous problem, I said you find the voltage, the phase angle of the impedance is equal to the phase angle associated with the voltage minus the phase angle associated with the current. The phase angle associated with the voltage is 40 degrees minus the phase angle associated with the current, which is 53 degrees. So what you end up with, the phase angle associated with the impedance is minus 13 degrees. Don't just call it 13 degrees, because you have to qualify it, lagging or leading. So we don't have to say lagging or leading here, because you know if the phase angle is equal to a negative, it puts it in a fourth quadrant. The fourth quadrant has to be capacitive. It's an RC circuit. Look through this problem again. Problems 5 and 6 were pretty useful problems. And finally, what I'd like you to do, I have two additional problems Now you can find these problems back in video 6D. Toward the end of video 6D, I labeled them problems 3 and 4. You don't have them in your lecture notes, but I think these problems are important. I'm not sure why I called them 3 and 4. They're really just some different problems that associate with these phase angles and using derivatives to calculate other parameters, voltage or current. So if you start at the 17-minute 40-second mark in video 6D, I have 2 additional problems, problems 3 and problems 4. I'd like you to make sure you understand those. So between the 2 problems we just covered, which were on pages 122 and 123 of your lecture notes, and these 2 additional problems that start at the 17-minute 40-second mark on video 6D, you should have a pretty good idea some problems I might give you on the exam or the quiz. And that concludes this lecture.